In this video, we're going to be talking about the dot product. Now, you may recall from what we did in Calculus 2 that we studied that when a force is applied to an object and the object actually moves, that the work done is the magnitude of the force multiplied by the distance that it moved. Now, in that case, we had to assume that the force was being applied in the direction that the object moved. We're now going to introduce the dot product, and we'll be able to discover that even if the force is not in the direction of motion, let's say it's off at an angle, that we can still find the amount of work done using the dot product. Now, let's think about a real-world example of when this might occur. You might have something like a child pulling a wagon. So the child is standing here and pulling the wagon in a slightly upward and to the right motion, but the actual wagon is moving horizontally. So the force is being exerted at an upward to the right angle, but the motion is this way. We need a dot product in order to find out how much of the force exerted by the pull of the child is actually working to move the wagon in the direction that it moves. And this will enable us to find the work done in moving the wagon by pulling it. Now, there are some other applications as well to dot products. For example, we can tell when two vectors are perpendicular to one another. And we'll also see that we can tell when they're either parallel or in the opposite direction. Now, let's go ahead and let me share my screen with you, and we'll get started on what is the dot product. Okay, so don't forget, if you're using the Word version of the file, that you can click up at the top and ask it to open the navigation pane so that you can see the topics we're going to cover in the left. Or if you're using the PDF file, open the bookmarks and you'll see the same information. So on the screen, you can tell what the learning objectives are. First, we need to define and calculate what the dot product of two given vectors is. Now recall that a vector has both magnitude and direction. So it's not just a magnitude, it's also the direction that it's moving. We're going to determine then whether two given vectors are perpendicular to each other. We can also tell if they're parallel. Now, the next thing we'll talk about are what are called the direction cosines of a given vector. We won't use the direction cosines all that often in this class, but we will use dot products quite a bit. And then we'll explain what we mean by projecting one vector onto another vector. This also gets used a fair amount. And finally, we'll look at an application of how to compute the work done by a force which is being applied, but not in the direction of motion. So we can't just do the force times the distance the object moves. The first thing we want to do, of course, is go ahead and define the dot product. So the definition of the dot product is right here. We have two vectors, and we're going to assume that we have three-dimensional vectors. This is Calculus 3, so we mostly want to deal with three-dimensional stuff. But would this be the same if you were dealing with a two-dimensional vector? In fact, it's the same if you're dealing with an n-dimensional vector. So this would apply in linear algebra, where you might have a 7-component vector, and you want to dot it with another 7-component vector. So in this case, what we have is vector 1 is u, which has 3 components, u1, u2, u3, and vector v, which has 3 components, v1, v2, v3, which are the x, y, and z coordinates, basically, of the terminal point if you have the vector in the standard position with the initial point at the origin. So the definition of the dot product that we actually use, there are two. This is the less formal one, but this is actually the one we use, is to take the dot product, and you'll notice it is literally a dot. You multiply corresponding components of the two vectors together. So the two x components multiplied together, the two y components multiplied together, the two z components multiplied together. And then you add those values together. Now, when you multiply the components together, you're getting a scalar, right? You're getting a constant. So when you get that constant and you add it to other constants, you're left with a constant. So the dot product of two vectors is a scalar. It's a number. It doesn't have direction. It's just a number like 5. All right. Let's go ahead and start with our first example, which is example 1. And we're looking here, we're trying to find u dot v. So in this case, we have vector u is 2, 9, -1, and v is -3, 1, -4. So to compute the dot product, we're simply going to, if I can turn on my color here, we're going to take vector u and we're going to dot it with vector v. So this is going to give me 2, 9, -1 in component form with the angled brackets, dotted with -3, 1, -4. Now, when you do the dot product, you do have to write the dot. You can't leave it off. It is required. So this basically gives me 2 times -3 plus 9 times 1 plus a -1 times a -4, which is going to give me -6 plus 9, which is 3, and then plus 4, which gives me a final value of 7. And you can tell again that the 7 is a scalar, right? So the dot product is this. Now, I know you're probably going, what is the dot product like in the real world? We'll get to that. But for now, we're just going to go through the motions of computing it, all right? So it's also an example of what's called an inner product, which you might see when you get to linear algebra. Now, let's talk about the properties of the dot product. It is a type of multiplication of two vectors, but it's not the only one. There are other types of multiplication of vectors. So it's very important that you put the dot so you know which type you're using. Let's suppose we have 3 vectors. We can call them u, v, and w. And let's let c be a scalar. When we're doing that, notice that we have u dot v is equal to v dot u. In other words, the dot product is commutative. So you can reverse the order. Why would that be so? Well, because multiplication of numbers is commutative, and to get the dot product, we're multiplying constants together. It also carries the distributive property. So u dot v plus w is u dot v plus u dot w. Scalar multiplication by a dot product, you could either multiply the first vector by the constant and then dot it with the second, or you could multiply the constant by the second vector and then dot it with the first. And remember, it's commutative, so order doesn't matter. Or you could take the dot product and then multiply the result by the constant scalar. Any of those will work. Now, let's look at v dot v. This is kind of an interesting thing. It turns out that v dot v gives you the magnitude of the vector squared. Remember, the magnitude of the vector is the square root of each individual component squared. But if I dot a vector with itself, I'm getting the square of each component added together, but without the square root. So it is the magnitude squared. Now, what happens if we dot a vector with the 0 vector? Well, the 0 vector is a vector of however long where all the components are 0. And since 0 times any constant value is 0, this gives us the scalar 0, not the vector 0. Remember, the dot product is a scalar. And then we have one more property down here, which says if 2 vectors are dotted with itself, 2 vectors the same, and you get the 0 vector, the only way that can happen if they're the same vector is if it is the 0 vector. So the only way to get 0 when you dot a vector with itself is if that vector is the 0 vector. All right, we're going to go through rather quickly, and we're going to talk about some proofs of some of these different ones. So these are all in the lecture notes, but we'll just go through a few of them right here. So let's take a look at the first one. On the first one, we want to prove that it is commutative. that u dot v equals v dot u, but we can only use the properties that we know, basically properties of real numbers, in order to prove it. So we start with the definition of u and v in component form, and then we take the dot product according to our definition, which is the addition of the multiplication of each of the corresponding components. So we get u1 v1 plus u2 v2 plus u3 v3. Now these are real numbers. Remember that the components of the vector are real numbers, and we know that real numbers are commutative. So I can switch the order because of the commutativity of real numbers, and then I can split them back apart, and this gives me v dot u, which is the proof of that part of the properties. Let's take a look at the next one, which is using distributivity, I guess. Yeah, the distributive property. So we have three vectors. We're going to prove it for the general case, which is that the vectors are n components long. So this would apply even in linear algebra. For us, most of the time, our vectors are 3 components long. So in this case, we've got our vector u, v, and w again, with their components with subscripts, so you know which one's which. And what we need to prove is that u dotted with v plus w, so dot product over addition of 2 vectors, is the same thing as u dot v plus u dot w. In other words, dot the 2 vectors and then add this together. So remember, a vector plus a vector is still a vector, but a vector dotted with a vector is a constant. So this is clearly a constant. And down here, the dot products also give constants, and a constant plus a constant is a constant. So I do have constant equals constant, but let's prove it. So the first thing you're going to do is we're going to take a vector dotted with a vector. So the first thing we do is what's in parentheses, which is to add the second 2 vectors together. So we have v plus w. So we add v1 plus w1, v2 plus w2, all the way to vn plus wn. Now, the next thing we want to do is take the dot product of these 2 vectors. So the vector u with the vector that is the sum of v and w. That means, by the definition of dot product, that I multiply the first component of each one together and add them all together. So the second components all the way out to the nth components are multiplied together. These now are all real numbers, right? Because they were originally components. Because they're real numbers, I can use the distributive property of real numbers to distribute the u1 over v1 plus w1 and the u2 over v2 plus w2 all the way out to the nth one. And this will give us the distributive property of the real numbers applied. Then I can go ahead and reorder things. So how am I reordering them? Instead of u1 v1 plus u1 w1, I'm doing u1 v1 plus u2 v2. So this one moves here, all the way down to un vn, which is out here. And then I'm moving all the ones with w's to the back. Now I can go in reverse, if you will, and say that this part right here, all the components of u and v multiplied together and then added up, is basically the definition of the dot product of u with v. And all of this part right here, which is the components of u and w multiplied together and then added up, is the definition of u dot w, which proves it. That's probably the hardest one to prove. Let's take a quick look at a couple more. So we have the constant multiplied by these. Again, if you take u dot v, then it's u1 v1, u2 v2, u3 v3. I'm using 3-dimensional now. And then a constant multiplied by that, well, these are all just real numbers. So I can use the distributive property to move things around and the commutative property to reorder the factors. And I can get any version that I want, which in this case is c times u dotted with v. Let's take a look at the next one, which tells us that if we dot a vector with itself, we get the square of the magnitude, which just makes sense because that gives you v1 squared plus v2 squared plus v3 squared, which is the magnitude without the square root on it. So it must be the magnitude squared. I believe we only have a couple more to do. This one is really straightforward. It says, suppose you have a vector, and I again use three-dimensional here, but it would apply to any dimension. And I multiply it by the zero vector of the same length. It does also have to be three-dimensional if v is three-dimensional. Then I get v1 times 0 plus v2 times 0 plus v3 times 0, which gives me the constant 0. Right? And then we have our final one right here, which is, suppose I have a vector v, which is v1, v2, v3, and dotted with itself, I get the 0 scalar, not a vector. Then that means that we've got to have, we want to prove that means the vector itself is the 0 vector. So by definition, v dotted with v is v1 squared plus v2 squared plus v3 squared. In this case, because they're all squared, they have to all be non-negative. So there's no way of reducing the sum. The only way the sum of non-negative numbers can come out to be 0 is if they're all 0. And that means that if they're all 0, that v1, v2, and v3 are 0. But if v1, v2, v3 are 0, then v has to be the 0 vector. Now, you probably won't be asked to prove these, but at this level in mathematics, you should be able to follow a proof like this. So let's now take a look at what you will be expected to do, and this would be to solve an application problem. So for example, we want to take a look at example 2. So when we're looking at example 2, we have vector p, which is 7, 0, 2, and vector q, which is -2, -2, and r, which is 0, 2, -3. You'll know they're vectors because they're bold-faced. When we handwrite, we'll use a harpoon or an arrow over it. So the first thing I want to do is find r dot p and then multiply by q. Notice there's no dot here between the parentheses and the q. Why not? Well, r dot p is a scalar. A scalar times a vector gives us back a vector, but we don't use the dot notation between a scalar and a vector. So first we're going to do the dot product. So we're going to have r dot p. So we've got 0 to -3 dotted with p, which is 7, 0, 2. And when we're done with that, we're going to multiply it by vector q. Notice that I put a harpoon over it because I'm handwriting it. Okay, so the next thing I want to do is take the dot product. So I multiply this component by that component, which would give me 0. And then I multiply this component by this component, which also gives me 0. And then I multiply the third component by the third component, which gives me -6. Notice that the dot product of two vectors is a constant, in this case, -6. And then I want to multiply that, not dot product, just straight up multiplication, multiply that by q. Now I can go ahead and write this as -6 times q, which is -2 to -2. And this would give me, as a result, that r dotted with p multiplied by q comes out to be the vector 12, -12, 12. Right? So hopefully that makes sense to you. Let's now go ahead and compute the magnitude of p squared. So the magnitude of p squared is just p dotted with p. So let me scroll up a little bit. So I've got p dotted with p, which is the magnitude of p squared. So this is just going to give me 702 dotted with 702. And again, at this point, you can start doing some of the work in your head. 7 times 7 is going to give you a 49. 0 times 0 is still 0. 2 times 2 is 4. So you should come up with 53. Let's now go ahead and do a geometric interpretation of what the dot product is. So what is the dot product geometrically? Like what does it mean? What are we doing? All right, so let's take a look at this now. Okay, so what we have here is two vectors, u and v, and there's an angle theta between the two vectors. Now, there are actually, in a sense, two angles between the vectors. The other angle goes around the outside and is larger than 180 degrees. But we're going to choose our angle theta so that it's always between 0 and pi, which sort of makes sense. No matter how you have two vectors, the furthest apart they can get is if they, well, point in opposite directions like this. And then they're 180 degrees or pi radians apart. So theta is always between 0 and pi inclusive. The formal definition of the dot product is that u dot v is equal to the magnitude of u, which is the length of the vector, multiplied, this is regular multiplication right here, it's hard to know how to write that up, times the magnitude of v, which is the length of that vector, times the cosine of the angle that's between them, or magnitude of u, magnitude of v, cosine of theta. And you can see now why we don't like to use the formal definition that much. The other way of doing the dot product is way easier, right? Just x times x plus y times y plus z times z. Yay, I'm done. So this is a more difficult method, but it will give you the same result. So if it's more difficult, why do we even talk about it? Well, it turns out that what we mostly use this for is to find the value of the angle between the two. In other words, we don't really use this definition to find the dot product. We use this definition to find the measure of the angle between the two vectors. So let's go ahead and prove this definition, and then we'll take a look at some more examples. So we're going to use the rules for vector subtraction, and we're going to find vector v minus vector u. All right, so we have the vector going from the tip of u to the tip of v, which is v minus u. So when we're looking at this one right here, we've got this. Now, we know that the lengths of the sides are the magnitudes, which is what we're representing when we put the vector in between the two vertical bars. And again, sometimes some books just use one vertical bar, all right, which it should be two, but it's okay. So in this case, we've got three sides to this triangle. We've got the length of the vector u, the length of the vector v, and the length of the vector v minus u, which closes that triangle. Now, this applies to multiple dimensions as well, even though I've drawn it in 2D. Now we can use the law of cosines from trigonometry. If we use the law of cosines from trigonometry, remember that the length of a side squared is equal to the square of the other two sides minus 2 times the length of the other two sides times the cosine of the angle between the other two sides. In other words, this angle theta is across from side v minus u. So looking at our picture up here, we can see that that is the case, right? That we do have angle theta across from v minus u. So we're using the law of cosines from trigonometry. Now, that gives us one representation for the magnitude of v minus u squared. But the dot product gives us another definition, which says the magnitude of a vector squared is the vector dotted with itself. So we're going to go ahead and dot these two vectors together. And we're going to do this using basically the distributive property. So we have v minus u, the vector, dotted with v minus, from this minus, v minus u dotted with u. So we are applying the distributive property. Then we can apply the distributive property again, and this will give us v dot v minus u dot v. And this one gives us v dot u minus u dot u, which also has another minus, and a double minus, of course, makes it plus. So when we write it out, we basically get v dot v, which is the magnitude of v squared, and we get two negative u dot v's. So we have negative 2 u dot v's, and we also have a u dot u, which gives us the magnitude of u squared. So we have one definition of what the magnitude of v minus u squared is coming from the definition of dot product, and we have another definition coming from the law of cosines. We now set the two versions equal to each other. So this is coming from the law of cosines. This is coming from the definition of the dot product. So then we ignore this. They're both equivalent to that. And we go ahead and, well, clean it up a little bit. So in this case, we want to solve for u dot v. So we're going to isolate the u dot v term, and we can subtract the magnitude of v squared, which will cancel that one, and subtract the magnitude of u squared, which will cancel that one. And then I've got a negative 2 here, so I can divide by the negative 2, and I end up with u dot v as the magnitude of u times the magnitude of v times the cosine of the angle in between them. And the QED, by the way, stands for quotidirat demonstratum, which means that which has been demonstrated or enough has been shown to prove it. So it basically is a marker for the end of a proof. So again, yes, that is the formal definition of the dot product, but not really the one we use to find it. When we have component form, we just multiply corresponding components together and add their sums. Now, when do we use it? We use this formula because we're generally looking for the angle between them. So we're looking for the cosine of the angle, or you can go ahead and solve it for theta by taking the arc cosine of it. So this is the form that may be the one that you want to memorize, that the cosine of the angle is u dot v divided by the magnitude of u times the magnitude of v, or theta is the arc cosine of u dot v over the magnitude of u times the magnitude of v. Now you may be worried because you know that anytime you use an inverse trig function, it's restricted, right? Remember, we had to restrict the domain of them. So when we're looking at this, we're a little worried, right, about what range we're going to get out of this. But again, remember that we defined theta to be between 0 and pi. The angle between any two vectors, however we want to do them, is going to be 0 to pi. And if that's the case, we're fine, because arc cosine is defined on 0 to pi, which is very convenient. So we don't have to worry about any issues or adjustments to the formula. Let's now go ahead and find the angle in radians formed by vectors a and b, and we're going to round to the nearest hundredth. So we have two vectors, a and b, and we want to find the angle that is in between them. So what we're going to have is the cosine of the angle theta is u dot v divided by the magnitude of u times the magnitude of v. And then, of course, we would have to take the inverse cosine. So in this case, our vectors aren't u and v, they're a and b, but it's about the same thing. So we're going to dot together 1, 2, 0 with 2, 4, 1. And we're going to divide by the magnitude of each one. So remember that to find the magnitude of a or b, we can come over here to the side. The magnitude of a is the square root of 1 squared plus 2 squared plus 0 squared, which would give me the square root of 5. and the magnitude of b is going to give me the square root of 2 squared plus 4 squared plus 1 squared, which would give me the square root of 21, I believe, if I'm looking at this correctly. Yep. So I can take these numbers and I can put them over here. Square root of 21. They're both square roots. I could multiply them together underneath there to get the square root of 105. And now I need to take the dot product of the numerators, the corresponding components. So 1 times 2 is 2, plus 2 times 4 is 8, plus 0 times 1. So what I'm getting up here is basically 2 plus 2 times 4 plus 0 times 1, which gives me, well, 10. All right. So rewriting this, I have the cosine of the angle is equal to 10 divided by the square root of 105. Now I want to find the angle itself, so I need to apply the inverse cosine function, and remember that this typically gives us something in radians. And so when I'm looking at this in radians, theta is going to be the angle whose cosine gives me 10 over the square root of 105. Because it's a positive number, I know it's got to be in quadrant 1. And this turns out to be, if you crunch it into your calculator, which you will have to do this one, turns out to be about 0.22 radians, which is really quite small, right? Remember that quadrant 1 goes from 0 radians to pi over 2 radians, and pi over 2 is about 1.57. So 0.22 is like really low, like 10 or 7 degrees, something like that, really small. Okay. Now that we've been playing around with dot products for a little bit, let's talk about some technology that we can use to explore these fascinating products. So the program that we're going to be using the most often this semester is called Calc3 D. It's a free online application to visualize and perform operations in basically in Calculus 3, in multivariable calculus. So it's created by Paul Seeberger at Monroe Community College. It's ongoing. And what we're going to do is we're going to click on the link. So this is the link spelled out in case the first one doesn't work. But if you click on either one of these, it should open up. Right? And then I've got some directions for you on how to explore what you're looking at. So let me get this to open up. All right. So it's loading. And you're going to get the home screen. Every time you go to Calc3 D, it's going to look like this. This is the home screen. You're always going to see this picture right here. It's always going to be this function. This is Calc3 D. So you want to bookmark this. This is going to be used constantly, almost daily in this course. So make sure that you have it bookmarked so you can find it again. We want to explore some information with vectors. We want to play around with vectors. So you're going to come up here on the upper left where the 3 horizontal bars are, and you're going to click on the 3 horizontal bars. You get a drop-down menu, and you want to click on the first option, which is File. And when you click on that, the first option there is View Vector Explorations. So click on that, and we're going to play around with vectors. Now, when you do that, you're going to see some stuff down here. So this is showing the vectors in 2 dimensions. And out here, you're going to see the vectors in 3 dimensions. It's preloaded with a couple of vectors. We want to go ahead and do free vectors. We want to enter our own vectors. So we're going to come over here, and we're going to click on free vectors. And then we're going to click on Vary Vectors in 3D. When I click on free vectors, it opens up this menu that you see down here. Now, if I don't click on Vary Vectors in 3D, then the default is just 2D. So if I come back to here and do free vectors, I just get 2D vectors. And I want 3D vectors, so I click on Vary Vectors in 3D. So you'll see the red, of course, is in red. It's spelled out for you. And you can also see the components, the X, Y, and Z. So what we want to do is take a look, for example, at the last problem that we did. I'm trying to think which one, or one of the problems that we did. Let's take a look at the dot product, I believe, is the one I wanted to do. So what you're going to do next, after you've clicked on vary the vectors in 3D, is you're going to come to where it says vector explorations, which is sort of here in the middle. It's a small box, but this is where you choose which application you want to use. So you're going to click on the down arrow, and you're going to come down to dot product exploration. All right, so let's see if we can find the dot product of a couple of vectors. So let's go ahead and take the first vectors that we put in, which was 2, 9, and -1. And you can click on the box and highlight, or you can also move the slider bars. The second one was -3, so you can move it and get a little bit more precise, but I just prefer clicking in the box. So I want -3, and then 1, and then -4. All right. And you'll notice that typically you do need to go ahead and hit enter in one of the boxes. While you're clicked into a box, hit enter to make sure that it's calculating what you put in. But you can see over here that it's graphed the two vectors for us, and it's giving me the dot product, and it's giving me the angle between the two vectors in both degrees and radians. I know you can use this to check your work. It's pretty awesome, right? And then if you come over here, you can click on the box and you can rotate it so that you can see the angle from different directions, so that you can kind of realize, oh, okay, yeah, that does look about like 81.5 degrees. I'll buy that, right? 1.422 radians. All right, so this is one exploration that we're going to do, and we'll be doing another one later in this video. Let's now talk about orthogonality, or what it means for something to be orthogonal, and how does that compare to being perpendicular. Now, when we talk about perpendicular, we're talking about being at literally a 90-degree angle. But 90 degrees only has meaning in 2D and 3D. 2D is just flat, right? So we can draw two lines that are at a 90-degree angle, and that's perpendicular. But you can also do perpendicular in 3 dimensions, right? Your walls are perpendicular to the floor and the ceiling, thank goodness. Otherwise, we'd all walk around kind of crooked. All right, so we've got perpendicular applying to 2D and 3D. Orthogonal is a more general word. If you're perpendicular, you are orthogonal. But orthogonal, you can be orthogonal and not be perpendicular. How does that work? Well, what if you're in R7? So your vectors are 7 components long. Well, perpendicular doesn't have any meaning in a 7-dimensional space, but orthogonal still does. So what does orthogonal mean? It just means that the product, the dot product of the two vectors is 0. Now, in terms of perpendicular, this makes sense because the dot product is the magnitude of each vector multiplied by the cosine of the angle. And if they're perpendicular, the angle is pi/2, or 90 degrees. And the cosine of pi/2, or 90 degrees, is 0. And 0 times any magnitudes is going to give us 0. So when the dot product of two vectors is 0, they are orthogonal. If they're in 2D or 3D, we also say they're perpendicular. But if we're in 7D, we just say they're orthogonal, right? Now, what about the word normal? Normal also carries this connotation of being perpendicular. So what does that mean? The term normal is generally applied for the relationship between a surface, some 3-dimensional surface like my arm, and a vector or a line in 2 or 3 dimensions. So if I had a surface, right, not just a curve or a vector, but an actual surface, and I had a line or vector that was perpendicular to it, we say it's normal to the surface, right? Meaning that the angle between the line or vector and the surface where they connect is 90 degrees or pi over 2. So again, perpendicular, orthogonal, and normal are related terms, but they do have slightly different meanings and connotations. Let's now take a look at the next theorem, which applies to orthogonal vectors. Now, this is an if and only if statement. If and only ifs work in two directions. So it says the non-zero vectors u and v are orthogonal to each other if and only if their dot product is 0. So to prove this, we have to prove both directions. We're told that the vectors u and v are not the 0 vector. So that's given. We want to show that if u and v are orthogonal, then the dot product is 0. And then we have to go in reverse. If the dot product is 0, then they have to be orthogonal. So we're going to prove both directions. So first, we're going to show the forward direction. U and V are non-zero vectors and they're orthogonal. We want to show the dot product is 0. Since they're non-zero vectors, their magnitudes are not 0. Well, then the only way that the dot product can be 0, given the formal definition, is if the cosine of the angle is 0. But if the cosine of the angle is 0 and the angle is between 0 and pi, the only angle between 0 and pi that has a cosine of 0 is pi over 2. And in 2D and 3D, that means they're perpendicular, which means they're orthogonal. So we've just proved that they are, in fact, perpendicular and that the dot product is u dot v. All right, now we want to go in the backward direction. Suppose we have u and v and they're non-zero vectors and u dot v is 0. Can we prove that u and v are orthogonal? So we've shown that if they're orthogonal, based on this definition, orthogonal means the angle is pi over 2. These aren't 0, and this is going to be 0, which proves that the dot product is 0. So now we're going backwards. Assume the dot product is 0, show that they have to be perpendicular in 2D and 3D or orthogonal. So in this case, by assumption, their magnitudes are not 0, which means by the definition, the formal definition, the cosine of the angle is 0, which means the angle has to be pi over 2, but that means that they have to be orthogonal. So we've proved both directions. Let's take a look at example 4. For which value of x is p orthogonal to q? So in order for them to be orthogonal, the dot product has to come out to be 0. So the first thing you want to do is dot p with q and get an expression. And then you need that expression to equal 0. So I'm going to pause the video here, go ahead and work out the example, then turn the video back on and we'll compare our results. Okay, so let's see how you did. Basically, to be orthogonal means that the dot product comes out to be 0, the scalar, not the vector. So we take the dot product of p and q, which gives us, when we simplify, the expression 2x minus 10. If they're orthogonal, the dot product is 0, so 2x minus 10 is 0, so x is 5. Hopefully this makes sense to you, and you were able to do this one on your own. Now, how could we tell if two vectors are parallel? In other words, the angle between them is 0, as in they're pointing in the same direction, or 180 degrees, meaning opposite directions, but still parallel to each other. If they're parallel, if the angle is 0, well, then the cosine of 0 is 1. So the dot product would be the positive magnitude of u times the magnitude of v. And then I would know that they are, in fact, in the same direction. If it's 180 degrees, the cosine of pi is -1. So then the dot product would be the negative product of the magnitude of u and the magnitude of v. Let's now turn our attention to some of the applications of the dot product. We'll start with direction angles and direction cosines, although we won't use these a whole lot in this course, but I do at least want to introduce them. You may see them in physics and other applications of multivariable calculus. So let's suppose we have a non-zero vector. I mean, we need a non-zero vector, otherwise it doesn't have any length, right? And points in all directions and no direction. So when we're looking at this, we have the coordinate axes, and then we've got this vector v here in red. So when we're looking at it, this vector creates an angle with each of the three axes. So we name these angles alpha, beta, and gamma. So this is alpha, this is beta, and this is gamma. And we name them in order of the relationship to the different coordinates. So the angle between the vector and the x-axis is alpha. The angle between the vector and the y-axis is beta. And the angle between the vector and the z-axis is gamma. So they're named in that order. The cosines of those angles are called direction cosines, right? So let's see an example of what and how this might get used. So when we're looking at these, here are the formulas for the direction cosines. So the formula for the direction cosine is coming from the definition of the dot product. So it's basically solving for the cosine of the angle. And you may say, well, yeah, but it's missing a magnitude. Yes, but it's v dotted with the I vector. The cosine of alpha is measuring the angle between vector v and the x-axis. And the standard basis vector that goes along the x-axis is I. And the magnitude of I hat is, of course, 1. That's why you don't see the magnitude of it down here. So basically just gives us v1 over the magnitude of vector v. Because I, remember, is 1, 0, 0 for in 3 dimensions. Remember that I hat is 1, 0, 0. So any other components are going to cancel out, and I just get the first component from vector v, which is v1, v2, v3, divided by the magnitude of vector v. Now, I can do the same thing for the direction cosine related to the y-axis, which gives me the vector dotted with the j vector. And remember, j hat is going to be 0, 1, 0. So it's the unit vector along the y-axis. And then, of course, the last one is k hat. And k hat is the vector 0, 0, 1. So it's the unit vector in the z direction. And these are our standard basis vectors. So when we're looking at these, this gives us what are called the direction cosines. Now, there's some interesting facts about these direction cosines. It's kind of weird, but if you take a vector which has as its components the 3 direction cosines, it actually turns out to be a unit vector whose magnitude is 1. And because the magnitude is 1, remember this would be the square root of cosine of alpha squared, cosine beta squared, and cosine of gamma quantity squared. But because the square root of 1 is 1, this also means that cosine squared alpha plus cosine squared beta plus cosine squared gamma is also 1, which is kind of weird. Which also means that since the magnitude of that vector is 1, the vector itself is equal to its magnitude, which is 1, multiplied by the vector, which is kind of weird. It's equal to its magnitude times itself. All right. Okay, let's take a look at example 5, where we want to find the measures of the angles formed by each pair of vectors. So we're going to start with the direction cosines, and then from the direction cosines, we'll find the actual angle. So I'll work through the first one, and then I'll pause the video so you can work through the second two. So we're going to start here between V and I. So this is really I hat, which of course is 1, 0, 0. All right. Vector V is in 3 dimensions. So I has to be in 3 dimensions as well. So the direction cosine is the cosine of alpha is equal to the vector V dotted with I hat divided by the magnitude of V times the magnitude of I hat. That's the definition of course, the dot product. We're using that to find the direction cosine. But in this case, the magnitude of I is 1, right? So you have 1 squared plus 0 squared under a square root, so it's 1. All right, the standard basis vectors are unit vectors. So this is just going to give me V dot I hat over the magnitude of V. But because I hat is 1, 0, 0, the second and third components, when dotted with V, are going to disappear. And I'm just going to get V1 over the magnitude of V. So this formula becomes V1 over the magnitude of V. So V1 is 3, and the magnitude of V, we compute that, would be the square root of 3 squared plus -5 squared, which is going to be positive, plus 1 squared, which would give me the square root of, well, let's just write it out, 9 plus 25 plus 1. I'm getting the square root of 35. Hopefully that's what you got at home. So when we're doing that, I've got that magnitude. So the direction cosine is cosine alpha equals 3 over the square root of 35. To find alpha, the direction angle, I need the arc cosine of 3 over the square root of 35. Because 3 over the square root of 35 is positive, I know it's got to be in quadrant 1. And when you work this one out, you'll come out with about 1.04 radians, which is about 2/3 of the way through quadrant 1. So it's around 61 degrees, something like that, 58 degrees, something like that. Okay, so now I'm going to turn you loose at home. Go ahead and pause the video and work out finding the second 2 direction angles, beta and gamma. Remember that when you use J, it's 0, 1, 0, and K is going to be 0, 0, 1. Pause the video now. So let's compare. To find the direction angle beta, which is between the vector and the y-axis, we first find the direction cosine. Now, because of the definition, we know that with dotting it with J, that we're only going to get the middle component V2 divided by the magnitude of V, because the magnitude of K is 1. This gives us -5 over the square root of 35. And since the cosine is negative and we know the angle is between 0 and pi, we're expecting it to be in quadrant 2. And sure enough, it turned out to be 2.58 radians, which is definitely between pi over 2 and pi. Pi over 2 is about 1.57, pi is 3.14. Then we do a similar thing to find gamma. And in this particular case, when we're looking for gamma, we again, because we're dotting this with the vector V with the k hat vector in the unit vector in the z direction, we only end up with the third component. And again, the magnitude of k hat is 1. So this gives us the direction cosine 1 over the square root of 35. And when we take the inverse cosine, we get about 1.4 radians, which is definitely in quadrant 1. So 1.57 is pi over 2. So it's quite close to pi over 2, but less than. So somewhere probably between 80 and 90. There's another application for the dot product, which is called projections. This is one that we will use from time to time. So I want to make sure that you get that. The direction cosines, direction angles, we don't use as often, but these we do use, particularly if you're going to take physics, you are going to need projections quite a bit. So the projection of one vector v onto another vector u can be thought of as the shadow of vector v casts onto the path of vector u. So notice in this case that vector u actually starts here and goes this direction, and the projection, which is written Proj subscript u, and then v back on the line, this is the projection of v on u. The one that is the subscript is the one that it's being projected onto that path. So notice that the projection is not directly on u, but is on the path of u. So if you were to extend u backwards, it would be on that part of it. Notice also that it is at a right angle, this connecting vector between the tip of v and the vector u is at a right angle, and that the projection of v onto you, like you're shining a flashlight, right? So you've got a flashlight up here somewhere, and you've got, oops, sorry, I think I just erased my flashlight. You've got a flashlight like this, and it's shining light down. And when it shines light down, it casts a shadow of the vector v onto the vector of u. And that's what the projection of v onto u is. It's like a shadow. So when you're looking at it, notice that the projection is coming from where both u and v start. So u and v are connecting right here. It's hard to see u, but u is actually also here. So this is u. I'm trying to draw it next to it, because if I'm on it, you won't see the projection anymore. So u starts here and v starts here. And the projection also has the same beginning point. And you have the same thing over here. V is here, u is here, and the initial point of the projection is at the same place. And then the projection extends along the pathway of u, either in the same direction, if the angle between u and v is complementary, right, less than 90 degrees, or in the opposite direction of u, along negative u, if the angle between u and v is supplementary, greater than 90 degrees, but less than pi. So here is our formal definition of the projection of vector v onto vector u. When we're looking at this, we can say that the magnitude of the projection, which would be the length of the shadow, is equal to the magnitude of v times the cosine of the angle. Now, why would that be? Well, let's come back up here to our picture and take a look at this right triangle. The magnitude is the length of this side. If this is our angle that we have right here, this angle theta that's between v and u, then the length of the red arrow is the cosine of that angle multiplied by the length of vector v, which is the hypotenuse of the right triangle. So remember that the cosine of this angle right here, so if I make that theta, the cosine of theta is going to be the hypotenuse over the adjacent side. And the hypotenuse is the length of it is the magnitude of vector v. And the length of the adjacent side is the projection of v onto u, right? So then I can simply solve for the projection of v on u. Did I do that right? I've got the magnitude of v over this. So hypotenuse over adjacent. All right. So when I'm done with that, that's going to give me the projection is equal to the magnitude of v times the cosine of the angle. Oops, I got that upside down. So at home, you're probably going, that's not right. No, you're right. It's not. So I've got it. I was thinking secant. So my bad. So this is adjacent. Oops, erasing and writing doesn't work. Over hypotenuse, which would be the projection of v onto u. And this is vector v. magnitude. And that will give me the formula that I need, that the projection of V onto U's magnitude is the magnitude of V times the cosine of the angle. Now, I already know that I can write the cosine of the angle using the formal definition of the dot product as U dot V divided by the magnitude of U times the magnitude of V. This relationship right here is from the formal definition of the dot product. But it's being multiplied by the magnitude of V, which means the magnitudes of V being scalars, constants, they cancel. And since they cancel, I get U dot V divided by the magnitude of U. So this is actually the length of the shadow. This isn't the vector, but it's the length of the shadow. It is a scalar. Now, to get the vector that's in that direction, I take the scalar and I multiply it by a unit vector in the direction of U or negative U, depending on which way it's pointing, depending on the size of the angle in between. So how do I get a unit vector in the direction of U? Well, a unit vector in the direction of U is just U divided by its magnitude. That will give me a unit vector of length 1 in the direction of U. So that gives me the magnitude of U squared. But wait a minute, we said the magnitude of a vector squared is the dot product of the vector with itself. So the projection of vector V onto U, V casting a shadow onto U, is U dot V divided by U dot U times the vector U. Now, this is probably the form that you will want to memorize, is that one right there. Now, the length of that projection is also called the component of V on U. It's a scalar. It's the length of that vector. And that would just be U dot V over the magnitude of U, which is just this part of it, not the unit vector, right? So let's recap a little bit. Scalars are numbers. Vectors are arrows with magnitude and direction. The projection is the shadow cast by a vector onto another vector. The length of it is the component of it. The vector itself is U dot V divided by U dot U times the vector U. Let's take a look at 2 examples. So in these examples, I've gone ahead and copied down the formula for you here, and I want you to find the projection of U on V, not V on U, but U on V. So which one is which? Let's go back to the formula and make sure we know which way it's going. So how do you know which one to use more often? Notice in the formula up here that U is mentioned 4 times and V only shows up once in the numerator. V is the vector casting the shadow. The one that it's casting the shadow on, that one is the one that gets used 4 times. So whichever one is written in the subscript position is the one whose dot product with itself you're dividing by and the one you're multiplying by. You need the unit vector in that direction, right? So if I'm asking you for the projection of U on V, then what I'm looking for, and this is just a formula for V on U, but the projection of U onto vector V would be equal to U dot V again, right? But the one casting the shadow only gets mentioned once, and that's U, whereas the one that it's casting the shadow onto gets used a lot. So you would be performing this. Remember that the dot product gives you a scalar. This is a scalar. Constant divided by a constant is a constant, but a constant times a vector is a vector. So let's go ahead and pause the video while you work that one out. And when you're done with that one, go ahead and move on to example 7, which is the projection of V onto U. Work both of those out, then turn the video back on to compare. Okay, so again, if you're going to do the projection of U on V, then u will only show up one time in the numerator, but v shows up 4 times. So it's going to be u dot v over v dot v times the vector v. And when you multiply all that out, work out all the algebra and arithmetic, you get this vector right here. Now we want to take the same two vectors, but instead of the projection of u onto v, we want to do the projection of v onto u. So when we're doing that one, the relationship changes. Since we're now doing the projection of v on u, v only shows up one time, but u being the subscript shows up 4 times. And when we work this one out, we get a different one. So go ahead, and you may want to pause the video and make sure that you've done the work correctly. When you're ready, turn the video back on, and we'll take a look at exploring the projection through Calc3 D. Okay, let's now take a look at this example in an exploration on Calc3 D. So we're going to come back to Calc3 D, and we're going to click again in the Vector Explorations box. And this time we're going to take the Projection Exploration option, which is down here at the bottom. So I'm going to click on that. Notice it kept my choices for free vectors and vary the vectors in 3D. Now it's got the red vector and the blue vector, but we want a projection. So unfortunately, in this particular case, you have to know which way Calc3 D is computing these. So let me make sure that you understand. Calc3 D always projects blue onto red. All right, so it's projecting blue onto red. So if we want the projection of V onto U, which is the last one we did, V onto U, then we need to have V be the blue one and U be the red one. So V in our case, which is going to be blue, this is the projection, V onto U. So V was 1, 0, and is it -2? V is -2. And U, which is what it's projecting onto, is 2, 1, -1. Right? And then I always hit enter just to be absolutely sure. And you can tell that what's happening is that the blue one is casting a shadow at a right angle to vector U here, and it's casting a shadow onto U, and you can see that it's projected that way. And up at the top, it's telling you what it turned out to be. And if we come back over here to our sheet, we had 4/3, 2/3, -2/3. And when we look at this, we're going to see that we're getting 4/3, 2/3, -2/3, which is correct. Now, what if you wanted to project the other way around? You wanted to project U onto V instead of V onto U. Then you would need to reverse which one is red and which one is blue, because in Calc3 D, it always projects blue onto red. Let's now take a look at breaking a vector apart into its component parts. When we look at breaking a vector apart, this is something that needs to be done quite a bit in physics. So when you're looking at it, you can break it apart into different components using the projection. So if we're using the projection, what we're actually getting are 2 vectors. We're getting the vector, which is the projection itself, and we're also getting a vector Q, which is the vector that is perpendicular to the one being projected onto. So notice that Q is coming here from the vector that we are projecting on. So the projection is here. So Q is perpendicular to the projection of V onto U. And it would be perpendicular no matter which type of angle you have between U and V, whether it's complementary or supplementary. All right. So when we're looking at this right here, we can see that if we add the vectors together, note that the projection of V on U starts where both U and V began and points out in this direction. If I add these together, that the projection of V on U plus Q should give me V. And it works over here in this case as well. The projection of V on U plus Q gives me the vector V. And this is a way of breaking the vector V down into two component parts, which a lot of times in physics, you want a horizontal and you want a vertical. So it makes sense to do this. And we can also think of right triangle trigonometry as doing something like that. So let's take a look now at example 8. In example 8, we want to express the vector 5i minus j as a sum of orthogonal vectors, so perpendicular to one another, since this vector, of course, is in 2 dimensions. So orthogonal as perpendicular, such that one of the vectors has the same direction as this vector right here. So if one of the vectors has the same direction as U, then it must be the projection of V onto U. And then we'll check their dot product to make sure that they are, in fact, orthogonal or perpendicular. So what we're looking for is the projection of V onto U and Q, the other vector. So again, let's take a look at the picture up here. So we're looking for both the red and the pink here, or the red and the blue here. So those are the two vectors we're breaking V down into. And it'll be the sum of those two vectors. So we need to find Q, and we need to find the projection of V on U. So let's note that first. Find Q and the projection of vector V onto vector U. And again, make sure you get that subscript down and below the line. So we need to find these two vectors. Well, first off, it's not too hard to find the projection right off the bat. So we can find the projection of V onto U. And remember, this is going to be U dot V, the dot product of the two vectors. The one that's on the bottom in the subscript gets written 4 times. So it's U dot U times vector U. So now I can rewrite these. I can also think of V as 5, -1. And I can think of U as 4, 2. So in this case, they're written in terms of the standard basis vectors. And in this case, they're written in component form. So in component form, we just multiply the corresponding components together. So U dot V is going to give me 20 minus 2 over the magnitude of U would be U dotted with U. So it's going to be 4 squared plus 2 squared, which is the magnitude squared. So that would give me 16 plus 4. So, and then I multiply this by vector U. So I'm getting 18 over 20, I think, times vector U, which reduces, of course, to 9/10. Algebra first, then you can do the other. And we're multiplying by 4, too. So the projection of vector V on top of vector U, or in the direction of -U, is going to give me the vector 36 over 10, 18 over 10, which is the same as the reduced vector 18/5, 9/5. Right? Now that's one of the vectors. That's the projection. Now I need Q. How do I get Q? So how do I break V apart into two vectors that are orthogonal to each other, perpendicular? May or may not be horizontal and vertical. They could be at odd angles, but we still want them to be perpendicular. So how do I find Q? Well, remember that Q plus the projection of V onto U is equal to vector V. So I can find Q by subtracting the projection from vector V. All right, so let's write that part down. So this implies that Q is equal to vector V minus the vector that is the projection of V onto U. So Q becomes V, which was 5, -1, minus the projection, which is 18/5, 9/5. And I would have to have a common denominator. So 5 with denominator 5 would be 25/5. So that would give me 7/5. And -1 would be -5/5. So -5 minus 9 would be a -14/5. And there are my two vectors. There's the projection, and there's Q. Now, the last part of this question is to verify that these are orthogonal to each other, that they are in fact perpendicular. So how do I prove that they're perpendicular? To prove that, I need to take their dot product and show that it gives you 0. So in our last step, we're going to dot these two together. So we're going to take Q dotted with the projection of V onto U and see if we get 0. So Q is 7/5, -14/5, dotted with 18/5, 9/5. Now you could factor the 1/5 out of the 2 and then not deal with the 1/5, but this is fine. So 7 times 18 turns out to be 126. So this gives me 126/25. And it turns out that 14 times 9 is also 126. And the denominator is 25. And that gives me 0, which proves that they are perpendicular or orthogonal to each other. Let's take a look at example 9, which is an application problem. So we have just a little bit left to do. So we want to take a look at example 9. We have a container ship. The container ship leaves port and is traveling 15 degrees north of east. So east is going to be directly to the right in a horizontal line. 15 degrees north of east means tilted up 15 degrees. Its engine generates a speed of 20 knots along that path. So the magnitude of the vector in that direction is 20 knots. But the vector itself is going to be different. We'll have to come up with a representation for the vector, which will relate, of course, to the angle. In addition, the ocean current is moving the ship southeast. So south would be directly down. East, of course, is to the right. So it's moving it in this direction at a speed of 2 knots. Now, southeast, without any degree modification, is going to be at a 45-degree angle. So it's down here in the middle of quadrant 4, right? Considering both the engine and the current, how fast is the ship moving in the direction 15 degrees north of east? So let's take a look at the picture now so that we can kind of get an idea of what's going on. So the current, which they've labeled W, doesn't make sense. It should be C for current, right? Okay, but at any rate, they've got the current, maybe the wind is making the current, I don't know. So we've got the current going this direction, which is pushing the boat both south and east. Now, the south part's not helping me at all, but the part that's pushing east is helping me. So there has to be a projection of this vector onto vector V. So the projection of W onto V, that component of it is helping to push the vessel along vector V. So what I have in my picture then is I have a projection, which I'm going to draw right here at a 90-degree angle, which is this vector right here. And let's make it pink, which goes right here. And this is the projection of W onto vector V. Now, the magnitude of that projection is going to be the speed at which it's projecting it in that direction, 15 degrees north of east. And so I need to take the magnitude of it and add it to my 20 knots, and that will tell me how fast the boat is moving in this direction. Now, I'm expecting it to be more than 20 knots because I know part of this motion is in the easterly direction, and that part is going to help the ship go faster this way, which sounds kind of crazy since this is mostly or partly south, but the part that's going east is going to help us some. So the first thing we want to do is we want to write down the magnitudes of the vectors that we have. So the magnitude of V is the 20 knots, right? That's how fast it's moving in that direction. And the magnitude of our current, maybe pushed by the wind, is 2 knots. So those are the measures of the magnitudes of the vectors. Now I need the magnitude of the projection of W onto V. But to do that, I have to have a vector for W and a vector for V. So in order to do that, I need to take a unit vector in that direction and multiply it by the magnitude. So I need a unit vector in that direction. Well, let's start with W, since that one is a little bit easier to understand. So when I'm looking at W over here, I need some kind of vector. The magnitude is 2, and I need to multiply by something that is in that direction, but is going to be a unit vector. Well, to me, that says cosine squared plus sine squared equals 1, and the square root of 1 is 1. So I want something that is going to be the cosine and sine of this angle. But this angle is negative 45 degrees. So in the x direction, of course, I want to move the cosine of negative 45 degrees. And in the y direction, I want to move the sine of negative 45 degrees. So I'm splitting W up into 2 components, which is the horizontal component and the vertical component. So like this, by using the cosine and sine of the angle. Now, we know that the cosine of a negative angle is the same as the cosine of the angle because it's an even function. And the cosine of 45 degrees is square root of 2 over 2, or 1 over the square root of 2. So I can represent this with just 1 over the square root of 2. But sine is an odd function. So sine of a negative angle is the negative sine of the angle. So this gives me negative 1 over the square root of 2, which gives me 2 over the square root of 2, negative 2 over the square root of 2. Right? Now, this is a unit vector because the cosine squared of this plus sine squared of that, you know that since the angles are the same, cosine squared plus sine squared gives me 1, and the square root of 1 is 1. I can use a similar idea to find a representation for vector V. So let's represent vector V now. So vector V is going to be equal to the magnitude, which is 20, times the cosine of 15 degrees and the sine of 15 degrees, which again, that will be a unit vector because of the Pythagorean identity for trig. Now, when I'm looking at this, I would have to multiply out what the cosine of 15 degrees and the sine of 15 degrees are. And we come up with, since we're rounding to about 2 decimal places, we come up with about 19.32 and about 5.18, right, for those 2 values. Now, the next thing that we need to do is we need to find the magnitude of the projection, which is the component of it, just the scalar part. So we need to find the projection of W onto V and find the magnitude of it. So there are different ways of computing that, but one of the formulas that we can use is here. So let's go ahead and use this. So the projection of W onto V is equal to the component of W onto V, which is equal to the dot product of W with V divided by the magnitude of vector V. Now, I know what the magnitude of vector V is. They told me it's 20 knots. So I know what this is. And now that I have an expression for W and V, I simply need to dot them together and divide by 20. So go ahead and grab your calculator and work that out. When you're done, you're going to get something that looks like 2 over the square root of 2, negative 2 over the square root of 2, dotted with 19.32-ish, 5.18-ish. You should carry more decimal places so that you can round appropriately, over the magnitude of V, which we know is 20. And when I'm done, I end up with about 27.32 minus 7.32 over 20, which gives me 20 over 20. And this is an approximation, right? And that gives me 1. What's 1? Well, let's go back to the picture. The projection of the current onto the path of the boat is 1 knot. That's the magnitude of it. Now, the boat itself can go 20 knots, but the current is pushing it 1 knot faster. So in this case, the ship is moving at 21 knots, right? And that is the speed at which the boat is going, faster than it could go by itself. We have one final application to be done, which mostly applies to our engineering and physics people, which gets back to what motivated our development of the dot product in the first place, which is how do you compute work done when the force is not being applied in the direction that the object is moving. So the classic example of this, of course, is a child pulling a wagon. The force is upward and to the right, but the wagon is moving horizontally. So the only part of the force that's actually producing the motion, of course, is the projection in the direction of motion. In this case, the horizontal component of the force. So when we're looking at this, how can we find the amount of work done? Well, it turns out that the component of the force onto the vector u is going to give us that magnitude of the force in the direction of motion. So u is the direction of motion, and the component of F onto u is the magnitude of that force in that direction, right? So again, this comes out to be u dot F over the magnitude of u, the magnitude of the direction vector. So when we're looking at this, we can use this to find the work done. Now, the work done, of course, is normally the force applied in the direction of motion multiplied by the distance moved. In this case, the force applied in the direction of motion is the component of the force in that direction along that direction vector. And then we have to multiply by the distance moved. So if it's moving from point P to point Q, what we end up with is the dot product of the force times the vector, which gives us the magnitude of F times the magnitude of PQ times the cosine of theta. Let's go ahead and put it in practical terms and work a very simple example. So when we're looking at a simple example, we have a constant force of 30 pounds is being applied at an angle of 60 degrees. So probably an adult pulling this trolley. So the angle here between the horizontal and this is 60 degrees. The horizontal is the direction of motion. The force is being applied this way. The force is 30 pounds. We're pulling the handcart 10 feet in the horizontal direction. What's the work done? So in this case, we need to find the component of the force in the direction of motion. So that's the component of the force on, in this case, S, where S is our horizontal distance. S is often used for distance in physics. So this is going to give us, of course, the magnitude of F times the cosine of the angle. This is the component of that measure in that particular direction. So when I look at this, the cosine of the angle, of course, is 60 degrees. So I have the magnitude of the vector F times the cosine of 60 degrees. Well, the magnitude of the force is the 30 pounds, and the cosine of 60 degrees is 1/2. So in essence, I would accomplish the same thing as if I applied a force of 15 pounds directly in the direction of motion, in a horizontal direction. So that's the component of the force that's actually helping the trolley to move. I know it's kind of crazy that half your energy is doing nothing. All right. So then we compute the work done, and the work is going to be the force times the distance moved. So we have 15 pounds times 10 feet, which is 150 foot-pounds, right, in the English system, right? So I hope that you have enjoyed this and learned something about the dot product. In our next video, I believe we'll be talking about the cross product, which also gets used quite a bit in multivariable calculus. Join me for the next video.